Hi, my name is Jordan Suter, and I'm Associate Professor in the Department of Agricultural and Resource Economics at Colorado State University. I'm going to be talking about some economic work that we've done to analyze groundwater use and conservation in the Ogallala Aquifer, along with my colleagues Dale Manning and Chris Gomans, also in the Department of Agri and Resource Economics at CSU. So by way of outline, I'm going to begin by talking about some of the general characteristics of the Ogallala Aquifer, and then get into some more specific details of producer preferences in the Republican River Basin of Colorado and some of the integrated modeling work that we've done to try to understand the trade-offs associated with specific policies that aim to conserve groundwater. Now, many of you are aware of the wide variation in groundwater availability across the Ogallala Aquifer. Here's a map of saturated thickness, one measure of groundwater availability, and how it varies from north to south across the aquifer. You can see parts of Nebraska and the Sandhills region north of the Platte River with over 1,000 feet of saturated thickness, and areas in the south and west portions of the aquifer that have less than 100 feet of saturated thickness. Now, if we look at the relationship between saturated thickness and some economic outcomes, like the percentage of land that's irrigated, you can see that saturated thickness has a dramatic impact. So here I show the counties that overlie the Ogallala Aquifer broken up into three categories: low, medium, and high levels of saturated thickness. And in the pre-development time period, before 1940, you can see that there really was no difference in the quantity of land that was irrigated across these three groups of counties. Now, after World War II and into the 1960s and 70s, as groundwater technologies and energy resources came available, there was a dramatic increase in the quantity of irrigated land and land irrigated with groundwater. But particularly that was the case in the counties with the highest levels of saturated thickness, where now nearly 25% of the agricultural land in those counties is irrigated, compared to less than 10% of the land in the counties with the lowest levels of saturated thickness. And from an economic perspective, that matters because the availability of water has an important impact on land value. So pre-development in the 1930s and 40s, there was no difference in land values in these counties in low, medium, and high counties with low, medium, and high levels of saturated thickness. But over time, there's been a big differentiation, so that counties with the highest levels of saturated thickness have the highest land values, and that water availability is capitalized into the value of land. So we know water and access to water is highly valuable. We also know that water availability is declining, and it's declining quite rapidly in portions of the aquifer, mostly in the south and western portions of the aquifer. So here's some results from Aaron Hacker and co-authors from 2016, and it shows that parts of the aquifer have lost more than 40 meters, I should say, of saturated thickness. So between 100 and 200 feet of saturated thickness in some areas. And if we focus in on Colorado and the Republican River Basin here, if you can see my pointer, the portions kind of west of where my pointer is lie in Colorado, the Republican River Basin of Colorado. And just between 2002 and 2015, there are parts of that region that have seen more than 30 feet, a 30-foot decline in saturated thickness. Those areas in Yuma County and down into Kit Carson County. Now, one way to measure water availability beyond saturated thickness is to think about what the capacity of the wells are to pump water. Essentially, how rapidly can they get water to the surface to irrigate crops. And there's wide variation. This map shows the wells in white dots that are located within the Republican River Basin of Colorado. And there's wide variation in their well capacities, with kind of an average well capacity in the 700 to 900 gallon per minute range, but a lot of wells that lie above 1,000 gallons per minute, and a large number of wells in these lower capacity levels below 500 gallons per minute. Unfortunately, over time, what we're seeing is more wells in this low category as saturated thickness declines, with as water use exceeds recharge, And along with that saturated thickness decline are declines in well capacity. Now, well capacity is very important for determining the quantity of groundwater used. Here's a graph that shows well capacity on the x-axis and average groundwater pumping between 2011 and 2015 on the y-axis, and you can see a strong linear relationship between those two. Now, well capacity also has a large impact on profitability. And so if you look at the left panel that shows the relationship that we predict between well capacity and profitability of a given well, you can see that below 700 gallons per minute on sandier soils, the profitability can drop off pretty dramatically. And that happens for a few reasons. The water itself is less productive because wells may not be able to keep up with crop water demands during particularly dry portions of the season. And it's also the case that producers are planting less irrigated land associated with a given well, and potentially crops that are less profitable, like wheat instead of corn. Okay, so for both sandy and heavier soils, we see that as well capacity declines, profitability can decrease rather dramatically. And so, knowing that well capacities are declining over time, we conducted a survey in 2016 of well owners and operators to understand what their level of concern was and what their preferences were going forward. So the median respondent to our survey operated 3 wells with an average capacity of about 750 gallons per minute. So we feel like those users are fairly representative of the general population of groundwater users in the region. And many of them reported declines of over 100 gallons per minute in their wells over the last 20 years. In addition, over 90% of respondents said they were at least moderately concerned about long-term availability of groundwater, primarily because they're concerned about future generations and the viability of their communities. And then many respondents suggested that they would like their groundwater management district to be thinking about policies that would seek to conserve water, with only 25% of respondents saying they would not be willing to give up economic returns to increase future water availability. So to think about policies that could be enacted, we look across the aquifer to see what conservation policies have been adopted in other regions. And groundwater use quotas or annual use restrictions are currently in place in both Nebraska and Kansas and portions of Nebraska and Kansas. And these typically limit the amount of water that a user can use over a 5-year time frame, with penalties if the individual uses more than that allocation. Irrigated acreage fees are currently in place in the Republican River Basin to fund the compliance pipeline. Of course, these fees could be increased to attempt to actually conserve water, and they would conserve water by urging individuals to switch from irrigated land to non-irrigated crops. And as a result, they would have the biggest impacts on portions of the region that have the lowest profitability. Those individuals would be what we would predict be the most likely to restrict their irrigated acreage as a result of irrigated acreage fees. Now, alternatively, groundwater use fees are in place in the San Luis Valley, and these fees charge users based on the volume of water they use, not necessarily the amount of land that they irrigate. And a nice feature of a fee like this is that it provides incentives for all groundwater users to reduce their groundwater use so as to reduce the fees that they owe. Then the final policy that we see implemented fairly widely is a retirement program, often through the Conservation Reserve Enhancement Program. And there are such programs in place in parts of Nebraska, Kansas, and Colorado. And of course, it reduces or eliminates water use from the wells that end up participating in that program. Now, when we have a program or a policy that includes fees, it is the case that we want to use the fee to conserve water, not necessarily to raise money. And so to deal with that and to reduce the financial burden on the producers that would be subject to a fee, you could actually make the fee into kind of a threshold policy where individuals that use more water than the threshold pay a fee on each unit above the threshold, and individuals that use less than the threshold would receive a subsidy per unit below the threshold. So, for example, if you had a threshold of 150 acre-feet per well, individuals that used more than 150 acre-feet would pay a fee per acre-foot above 150 or receive a subsidy for every acre-foot below 150. And over time, you could actually adjust that threshold so that the policy would be budget balancing. The fees paid out would essentially, or the subsidies paid out would essentially be paid for through the fees that are brought in, so that you're not raising money or losing money over time. Now, to understand the impact of these policies, we really need a comprehensive look at how they impact behavior of all water users, not just the individuals that participate in the program. Because water that's saved at one point means additional water availability for others nearby. And so we want to understand how the policies impact the behavior of all groundwater users in the basin. So to do that, we're going to use an integrated modeling framework where we have an economic model of individual decision makers choosing how much land they irrigate, what crops they grow on that irrigated land, and then how much water they apply to those crops. And that economic model is going to be informed by an agronomic modeling structure that dictates the trade-offs of water and yield as a function of soil, climate, and water attributes. Okay, so the economic model is informed through the agronomic trade-offs that the individual faces, and then the economic decisions associated with overall water use feed into a hydrologic model so that we can understand over time how the economic choices of water use translate to changes in water availability, and then how those changes in water availability impact the economic decision making in the future. Now, to begin, we run this modeling framework in the Republican Basin to understand what a business as usual scenario would look like. If we don't change anything, we know that water availability is going to continue to decline. And as water availability continues to decline, it's going to reduce the profitability because of declining well capacities. So what we predict is that over time, we'll see over a 50-year time frame, we'll see a 20% reduction in average profitability per well, with corn acreage declining by approximately 25%. Now remember, that's an average. There are going to be a lot of wells where profitability declines less than 20%, right? Their well capacities remain relatively high, but unfortunately, we're going to see some wells that have profitability declines that are much more than 20%. Now, to assess the impact of alternative policies, we want to compare those policy outcomes to the business as usual. And in particular, I'm going to compare policies that implement quotas or water use restrictions, irrigated acreage fees, and groundwater use fees. And the basic finding is that, yes, all three policies can be useful in increasing saturated thickness levels, but they all do have negative impacts on profitability. The differences between policies and between regions, however, is very important. So just a snapshot of results, and again, I'm happy to provide more detail related to these results. If we implement policies that seek a 10% reduction in water use below current use scenarios, what we see is that an irrigated acreage fee tends to result in the lowest quantity of saturated thickness saved after 50 years and the highest cost, right? So our suggestion would be to not use an irrigated acreage fee in an attempt to conserve groundwater, but rather look more at a quantity restriction or quota or a pumping fee, which after 50 years is found to result in more water in the aquifer and a fairly low impact on profitability, reducing the net present value of profits over that 50-year time frame by less than 5%. And indeed, a large percentage, nearly a quarter of all wells, actually benefit from the policy because there's more water available in the aquifer. Their profits increase as a result of the policy over that 50-year time frame. Now, as I said, another option would be to go with irrigated land retirement. And these land retirement policies pay individuals an annual payment over 15 years typically to take their wells out of production, typically in perpetuity. And our analysis of the Conservation Reserve Enhancement Program in Colorado suggests that the wells that have participated tend to have low saturated thickness and relatively poor soil quality. They have the lowest opportunity costs of participating, which is not a bad thing. It leaves more water for wells that are profitable, and so that may very well be a very good outcome associated with the policy. But it's also clear that these policies are expensive. The cost of retiring an individual well is on the order of $200,000 to $300,000 over the lifetime of a contract, and the benefits from that well retirement that leaves more water in the ground tends to increase saturated thickness levels within a 5-mile radius of the well that's retired. And so what we know is that because saturated thickness levels are higher near retired wells than they otherwise would have been, those neighboring wells tend to use more water. So they tend to get the benefits of the retirement program. And I think of a well retirement program more as a water retiming program. It's retiming water from the current time period to the future time period, but it's unlikely to save a dramatic amount of water in the ground simply because the water resource is shared. And any water that's left in the ground because of retirement will at some point be used by the neighboring wells and lead to benefits to those wells. We've been doing some work that tries to estimate what those benefits are and potentially compare them to a policy that might use the same financial resources to pay individuals to have smaller reductions in water use across a broader set of users rather than retiring individual wells. So in terms of concluding thoughts, I think the most important thing is that in order to really understand policy trade-offs, we need to know not just how the policies affect outcomes in the near term, but really how they're going to affect the groundwater resource and economic returns over the long run. And to do that, we need to integrate human decision-making with aquifer dynamics to see how each responds to changes. A second point, as I just mentioned, is that in general, policies that can induce small reductions by a larger number of users are going to generate conservation outcomes at a lower cost than policies that induce conservation from a small subset of users. And finally, policies really need to be calibrated to individual areas. There's so much heterogeneity across the Ogallala Aquifer and even across the Republican River Basin of Colorado that a policy that may be best in one location may not be the best policy in another location. So I would urge policymakers to try to understand how those trade-offs vary locally to calibrate and choose the best policies for specific regions rather than having kind of blanket strategies that attempt to implement the same policy across a wide study area. So I thank you for the time, and I look forward to hearing some of your questions and comments during the session later today.